In this video, we're going to look at how we can generalize some of the earlier ideas we looked at about slicing objects and apply it to new scenarios where we're still trying to get a total, but to get to that total, we need to look at how we can build it up by looking at small pieces of a puzzle. Earlier, we looked at total area or total volume. This time, we're going to be looking for a total mass. Here's a scenario. We have a metal rod that is 2 meters long, and that rod has a changing density depending on where we are. The density is 3 at the start point, kilograms per meter, and at the other end, by the time x equals 2, we would have 4 kilograms per meter density. Now, if our goal is to compute the total mass, the question then becomes, why can't we simply look at the units, kilograms per meter and meters, multiply those out, and get a mass as an end result? Take a look at the options to consider here, pause the video, and then we'll check in. All right, the key issue here is definitely A. When we say multiply by the density, we can see already in our diagram that there's 2 densities at least. In fact, we know the density is changing all the way along the length of this rod, so there's no way to multiply by the density. Fortunately, we'll be able to address that like we've addressed earlier scenarios by looking at small pieces of this rod and accumulating the mass that way. Some people might be a little concerned by the units of the density. Oftentimes, kilograms per cubic meter is a more traditional length. Often units of kilograms per meters cubed or mass per unit volume would be more traditional, but it makes complete sense to talk about a length of chain weighing a certain amount, or if we looked at areas, a certain area of plywood weighs a certain amount. And so we don't necessarily have to have volume in terms of density. We can have mass per unit of something else and still have it be a reasonable density measure. Let's take a look next at how we can take this formula, which does make sense when the density is constant, and apply it to the rod we're looking at here. Our process is going to be to break this rod down into small segments, and not a big surprise here, delta x wide. And what we can then do is talk about a slice that's x away from the left edge, delta x thick, and on the slice, what we are accomplishing by taking a very small slice is that the density is approximately constant. What does that get us? It gets us the ability to use our mass equals density times the length. The key thing is this length is very small. Unlike the original scenario where we would have contemplated taking the entire length of the whole rod, 2 meters, if we have a small enough length, then this density is approximately constant. So we just add this little codicil here to our mass. It's the mass of a slice, and we know what that density would be. It'll be 3 plus 0.5 x's, and the length is delta x. Do a quick check on the units. This is density in kilograms per meter. This is a small length of the rod itself. That will be in meters, and so we're going to get kilograms when we're done, or the mass of a slice. We then expand this to get the total mass of the entire rod. And that would be what we would get if we added up all of these slice masses. So to get the total, we just imagine taking all the slices from the start to the end and accumulating those with the summation, but each slice has a very specific and very simple formula. We could go into more detail on this, but the natural thing to get the exact answer is to move this to an integral as quickly as possible. We'll do that on the next page. When we have our Riemann sum for the total mass, it's approximately equal to the sum of our density, 3 plus 0.5 x's times delta x, or we can get the total mass, which is exactly equal to all of these same ingredients, except the delta x gets converted to a dx. In our notation, we think of that as a very, very thin slice, dx thick, and the integral starts at the left-hand end of the rod, that's x equals 0, ends at the right-hand end, which is at x equals 2, and we're ready to go. Notice again the units are still here. We think of this as a density in kilograms per meter, and the dx still represents a distance, a little thin increment of distance, also in meters. Now that we've built the integral, we can now evaluate or integrate. Here that gives us 3x plus 0.5, add 1 to the power, divide by the new power, and evaluate that between 0 and 2. And that'll give us 6 plus 1/4, the 0.5 and the 2, and then 2 squared. And all of that minus 0 plus 0. Altogether, that gives us 6 kilograms plus 1 kilogram, or 7 kilograms, is the mass of the rod. Perfect. So we went from a problem where we couldn't use a simple formula for the density times length because the density was changing, but we could incrementally consider the density as we move along this rod, and on each little interval talk about the mass as density times a small unit of length, using the integral to add up the grand total to give us that 7 kilograms. Now, it's always a good idea to do a sanity check on our answers. We have 7 kilograms as our hypothesis here, and that is correct. But can we reassure ourselves that that makes some sense? Absolutely. At the end of the rod here, the density is 3 kilograms per meter. At the density here, at the far end, it's 4 kilograms per meter, 3 plus 2 times 0.5. And just from the form of the density, we had the density increasing from left to right. What that means is that the smallest density on the entire rod is 3 kilograms. So the total mass is certainly going to be greater than what we use as the minimum density times the total length. And this is similar to what we did with estimating integrals before, but now in a more physical scenario. If we take the lowest density over the whole thing, multiply it by the total length, well, that's 3 kilograms per meter times 2 meters, 6 kilograms. So we expect our total mass certainly to be greater than 6 kilograms, and in fact our answer was 7, so we get that. We also expect our total mass to be smaller than the highest density times the total length. And in our scenario here, the highest density we ever reach is at the far end here at 4 kilograms per meter, and still over that 2 meter length. So we get a maximum or upper end for the mass of 8 kilograms. And so our actual answer of 7 kilograms fits comfortably in that range. Validating the ballpark figure, at least for what we obtained. But the process we used here is absolutely correct. We're just checking for numerical accuracy or any possible numerical calculation errors when we do this reference check here.